We'll see how this turns out. So today we got to talk about significant figures. We've kind of started in on that idea by showing you guys how to measure, how to take a look at what the smallest what the smallest line is on a measuring device, and then guessing one digit past that line. Okay, so significant figures has a little bit more to do with mathematics and how it's a statistical tool. Okay, so here's sig figs. It's just going to sound like I swore and I got edited, right? Okay, that was the tardy bell for halfway, right? Okay, so sig figs here. The term sig figs or significant digits, people go back and forth and say one or the other, refers to digits that wind up getting measured. So you guys all just turned in a lab to me with a whole bunch of significant digits, I hope. As long as you made sure to have your known values and your one unknown, your guess digit at the end, that uncertain digit, as long as you have all those digits in each of your measurements, you should be doing pretty good. Okay. We do wind up rounding numbers sometimes when we do math, and we need to pay attention to how many sig figs there are. Otherwise, we can wind up overstating the accuracy of our answers. Okay. This is actually going to take us a couple of days to talk about and get through, because it's a new concept for you guys. You've never had to do this before. And quite frankly, it's difficult to get your mind around. Bless you. We'll see if we could hear the sneeze. I'm not going to say who sneezed. She might not want her name called out. All right, so here we go. Next slide here. You guys know this one, right? What's the value of pi? Circumference over the diameter, right? And when you calculate that in a calculator, the calculator spits. Oh, actually, you can't do that in a calculator because the calculator only spits out 10 digits, right? But a computer would spit out 3.14156.152653897932338, blah 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 blah, right? Whole bunch of numbers. What's that? A math teacher would tell you it's endless. I would tell you that it's not endless. Okay. It doesn't even actually stop at 3.14 in the example that I'm giving here. So Monday we're going to learn how to do the math and how to do the rounding. But for right now, I just want to kind of show you guys. I've got a number here that has 2 significant digits in it and a number that only has 1. 22 centimeters over 7 centimeters, right? That's what I would get for a circumference in a diameter. If I divided those and I'm following sig fig rules, I only need 1 sig fig in my answer. If I try and say that there's more, then I'm trying to say that my original measurements were using a ruler that had more precision, right? A ruler that has more precision, what kind of measurement can I get out of it? Would I get 22? If it had more precision, I'd get something like 22.0 maybe centimeters, right? So I'd use the same ruler to measure the second time, and I get 7.0 centimeters. That would give me 3.1 as an answer. Okay. Notice the best I've got is 2 sig figs here, and here I've got 2. I'm telling you, you only have 2 sig figs. Do you guys believe me? We probably have to go over how to get 2, right? If I wanted to get this many sig figs in an answer, I'd have to have a ruler that could measure all the way out to, what is this place value out here? Can anyone tell me what that place value is all the way at the end? I got no idea, right? You'd have to have a ruler that was precise to that place value in order to record that as a good answer. Otherwise, you're overstating the amount of precision that's available in your measurements. Okay. We'll review that again next week on Monday. Okay. But for right now, what you guys need to know is how to recognize sig figs. Okay. There's a couple of very simple rules as to how to do that. Okay. First rule is that non-zero numbers are always significant. That sounds pretty simple, right? So a number like 1,356, if it was a measurement, it winds up having 4 sig figs. The number 82, if it was a measurement, has 2 sig figs. Man, my notes stink. These things should be measurements, right? What am I missing on these things? Well, yeah, I'm missing labels. So let's see. I'm going to call this meters, and I'm going to call this meters, just for the sake of being easy. All right, they're both in meters. That's pretty comprehensible, right? Non-zeros, significant. The second rule talks about zeros. Actually, most of the rest of the rules talk about zeros. This one talks about zeros that are between non-zero numbers. Okay. If a zero gets sandwiched in between two non-zero numbers, like in 101, 101, that zero is automatically significant because it's between significant digits. Okay, so 101 would have 3 sig figs. Number that's given there, 10,023, it has to be a measurement again, so I better fix my notes later, right? 10,023 has 5 sig figs if it's in meters or any other measurement. Holy shnikes, this is a big number. I'm going to put some commas in here. There's a comma here. There's a comma there. 12,089,000, all of those zeros are sandwiched. Since they're sandwiched, they are significant, so that has 8 sig figs. Yeah. Next rule, leading zeros are never significant. So zeros placed in front of a non-sig fig never, ever, ever get counted as being significant. Are they important? Yes. Are they significant? No. Significance is a definition. Okay. So for instance, this value here is 0.00000025. I'm going to call that meters again. None of these zeros are what we call significant. Are they important in telling us the value of this measurement? Oh, heck yeah. They're important, but they're not significant. Significance is a formal definition for statistics here. Okay. And then finally, 0.02531 meters. That's only got 4 sig figs because you don't get any sig figs until you hit the 2. 2, the 5, the 3, and the 1 are significant. One more, trailing zeros. So zeros on the other side of the number, the right-hand side, are not significant, and this one's got an unless there's a decimal present. Okay. There's 2 examples here, and I'm going to actually add a third one written down. The number 12,000, again, this has to be a measurement. 12,000 meters winds up having 2 sig figs. Whereas the number 12,000.00, the 1 and the 2 are significant. Because the decimal is here, all of the zeros that trail wind up being significant. So we say there's 7 sig figs there. Again, here we go. All right. So what we're seeing here, guys, is this. The zeros in the front are never significant. So this 0 is not significant, that 0 is not significant, and that 0 is not significant. The 2 is significant, the 5 is significant, the 3 is significant, and the 1 is significant because of the first rule. All right. The fourth rule says trailing zeros are not significant unless there's a decimal present. Is there a decimal present? Yeah. Does it matter where the decimal is? It just has to be present. So these last 2 zeros are significant. 1, 2, 3, 4, 5. I'm seeing 6 sig figs there. Okay. So the last rule is all digits in front of an exponent are significant. So if you're writing in scientific notation, anything in front of your exponent, in front of your times 10 to the power, is significant. So the number 5.0500, that's going to have 5 sig figs. How does this relate to the measurements you guys just made? Significant figures in a measurement include all of the certain figures plus the uncertain digit. So every single measurement you made, I should be able to look at it and just count the number of digits that's in it, including zeros, and that will be how many sig figs you guys have, okay, for every single measurement in that lab you just did. When making a measurement, remember, you should only estimate that one digit, and the last significant figure in the measurement is the uncertain figure. That's what it's called. It's called the uncertain figure. Did I say that yesterday? Yeah, or the day before? Oops.